Well, thanks for the introduction, and thanks for having me, and also to all the speakers so far. It's been really interesting. So I will be talking about Hamiltonian simulation today. So given some system with some Hamiltonian h and some initial state psi of 0, we want to know what state the system is at a later time t, and we want to do that on a quantum computer because it might be classically not a tractable problem. So for the purpose of this talk, I'm going to assume a Hamiltonian of this form, where it's a weighted sum of operators. These alpha L's here are real and positive scalars, and these HL operators are available as gates or gate sequences on our quantum computer. And I want to focus on electronic structure calculations for the purpose of this talk, which, say, if you want to do quantum chemistry and we start with some molecule and we want to calculate its properties, we usually start with the Born-Oppenheimer approximation. So we fix the nuclei and we write down the Hamiltonian of the electrons in that potential. And then we do our Jordan-Wigner transformation or our Brevik-Kitaev transformation, and we end up with a Hamiltonian that is the sum, a weighted sum of some Pauli strings. And what typically happens if we do this is that the magnitudes of these coefficients, these alphas here, they vary greatly in magnitude. So we usually have a few very large terms, then some intermediate, and a lot of small terms that are too large to be neglected, but they're very small individually. And so this is the type of Hamiltonian we want to tweak our approach to. But first, very briefly, historical note. So the earliest known way to approximate this time evolution is by Trotter-Suzuki type or product formulas. So they all work pretty much like this. We have this exponential of our sum, which is the Hamiltonian, and we approximate it by just the product of the individual exponentials. And this is exact up to order t, and then plus some terms t squared times the commutators of these HL terms in here. And there are, of course, more elaborate, more complicated versions of this that are exact to higher orders. But what they all have in common is that the gate cost to implement them is always polynomially in the inverse error that we're making. So when I speak of errors in this talk, I always mean the distance of the operator we're implementing to the exact time evolution operator in some metric. So these are product formulas, and the reason they're so popular is because products come very naturally to quantum computers. Whenever we apply gates in sequence, we really apply the product. But there is an alternative to this, which was introduced in 2012 by Childs and Wiebe, which enables us to actually apply a sum of unitaries instead of their product. And because the sum of unitaries is in general not a unitary, this could first only be done with a probability that's smaller than 1. For our purpose, there is a way around this, which I will get to later. And this new technique sparked the development of a whole zoo of new approaches that are usually grouped together as post-Trotter methods. And they include things like quantum signal processing and qubitization, which some of you might be familiar with. But what I want to talk about today is one of the most straightforward and direct applications of this linear combination of unitaries, or LCU method, which is the truncated Taylor series. So we have our Hamiltonian again here, and the idea now is to expand this exponential directly into a Taylor series. So this was first proposed by Berry and colleagues, and they use the truncation of this form where they say the time evolution operator is approximately equal to this u sub n, where n is the order that we expand, that we use the Taylor expansion to. So this is a regular Taylor expansion. We have the sum up to the order n here, and then we just truncate all the rest. And they showed that this approach, because of this factorial down here, and because there is an efficient way to implement this as a quantum circuit, this scales exponentially better in the inverse error than the product formulas. And now what we did is we used a slight generalization of this formula, which you can see here. Instead of this u sub n, we have an L vector here. And this L vector has elements Lj that appear in this inner sum here. And because the alphas, so we assume that the alphas are sorted now. So alpha 0 is the largest term, and they're just monotonically decreasing. And I mean, we can always do this because it's just a sum. In this inner sum now, we don't sum over all the terms, but we only sum over the Lj largest terms in order L, in order J, excuse me. So by using this form of the approximation, we get a finer control which terms to include and which to exclude. And the motivation behind this is if we have a Hamiltonian, as I described in the beginning, where we have some terms that are very large and a lot of small terms, we might want to keep the large term to a high order, but start discarding the very small terms already at a very low order. And this is what this form of the expression allows us to do. So next I wanna briefly motivate how this whole LCU business works. Even though some might be familiar with this technique already, I think it's still worth briefly going over it. And for this purpose, we will rename all the terms in here. So we collect all the real positive coefficients, the alphas, the t to the k and the k factorial, into new real positive scalars beta j, and all the products of the operators and the minus I to the k get collected into new operators vj, just to make the notation a bit simpler. So this whole LCU method is really based on two operators. They are the select and the prepare operator. And here, the select operator, which we call S, acts on a product state. So the psi is our system state, and the J is an ancilla that we artificially introduce. And this S operator looks at this J state and applies Vj where these indices match to the system. So this Vj is the same as we had on this previous slide, this operator here. And this J is just the index that we sum over here. And the other thing we need is the prepare operator, which acts only on the ancilla. And the only thing we need to ensure is that if we act with this prepare operator on the ancilla 0 state, it puts it in a superposition like this, where it sums over all our indices J, and every state J gets a weight that is proportional to the square root of this coefficient. And of course, this needs to be normalized. So S is just a sum over all the beta J's. And with this, we can introduce this new operator W. So here it is again. And if we check what this does, if we apply it to a state of this form where the ancilla is initially in 0 and we have our system state, then you can imagine this prepare first puts this 0 into a superposition of all the indices. Then the select operator comes along and it applies the operators Vj to the appropriate system states. And then with this P dagger, we just uncompute this prepare operation. So each term gets another factor of square root of beta j. So now we have a sum over all the beta j's times these operators Vj, which is exactly what we defined as this U sub L. So this is already what we really want. But because this P needs to be unitary, we get this normalization factor out front here. So we get the state we want with the amplitude that's less than 1. And we get some garbage state here, which we only know the whole thing is normalized. And this garbage state has an ancilla state that is orthogonal to 0. That's all we know about it. So the naive approach here would be to just post-select on the ancilla 0 here. So we would measure the ancilla. If it's 0, we succeed. And if not, we fail and we have to try again. But even if we use the truncated Taylor series approach, we're going to slice up the simulation time into lots of small time steps. And if we do this post-selection, that would exponentially suppress our success probability. Fortunately, there is a way around this, which was also introduced by Barry and colleagues, which they call oblivious amplitude amplification. And it works very similar to regular amplitude amplification, but instead of reflecting about the initial state, we only need to reflect about the ancilla 0 state, because we know this property is true, that what we want has ancilla 0, what we don't want does not have ancilla 0. So it's very much like amplitude amplification, where we have this operator that we want to amplify, and we have it interleaved with these reflections in here. But these reflections, as I said, are only about the ancilla 0, which is very easy to implement. And now, if UL were really a unitary, and S would equal 2, so remember, S is the sum over all the betas, and these betas are functions of T. If we go back, you can see these betas here, they contain this T to the K. So we can adjust the time step size to ensure that S equals 2, but UL will not be exactly a unitary, because we have to truncate at some point. So UL will only be close to a unitary. And then what we really apply with this operator is this object here. And if we want to know the accuracy of our method, we have to calculate the distance of this object to the exact time evolution operator. Now, I don't have time to go into the exact circuit construction, but I can tell you that there is an efficient way to implement this as a sequence of gates, and that the cost it takes to implement it is proportional to the one norm of our L vector. So that is just the sum of all the terms we included in our expansion. And another important aspect is that we can bound the error that we're making in our expansion by a very simple expression that is classically tractable. So it's very easy to calculate on a regular classical computer. And so with these two things, what we did was we start with an empty expansion. So we just include no terms, it's just the identity. And then one by one, we check all the orders, because it's classically tractable. We can just try all the orders and check which order we should add a gate in to decrease this error bound the fastest. So at first, we're going to add the largest term in the first order, but then we check whether it's better to add the second term in the first order or add the largest term in the second order. So we do that iteratively, and you can see this as sort of a greedy search algorithm that just in each step takes the largest decrease. The largest decrease in the error bound. So now I want to show some results that we obtained. And because the efficiency of our modification depends crucially on the distribution of these alphas of the coefficients, it's very difficult to get any meaningful analytical results. So all analytics work out to be the same as for the, I'll call it the canonical method by Barry and colleagues. And these coefficients for quantum chemistry, they're usually results of some numerically done integrals, so there are no analytic expressions for them usually. So what we did is we just collected a bunch of molecules, and we did what I explained at the beginning. We took their equilibrium position, we added in the electrons, we got the electronic Hamiltonian in second quantization. We did a Jordan-Wigner transformation, and then we ended up with these Hamiltonians that are just weighted sums of Pauli strings. And we calculated the errors for the small molecules. So here is an example. This is hydrogen fluoride. This has 11 qubits. And vertically here, you can see the error. So this is the distance of the operator we're implementing to the exact time evolution. And horizontally here is the cost of implementing that. And well, first of all, you can see it converges exponentially as is expected. But then you can see the dashed line is the error bound for the canonical one. And the solid line is the error bound for our modified version. You can see in the beginning, it decreases a lot faster, and then it kind of just goes parallel. And so we gain an advantage over the canonical method here in the first order. So this is in multiples of orders. And then we just kind of keep that advantage all the way down. And what is interesting is, so these squares are the exact errors of the canonical method, and these circles are the exact errors of our method. And you can see that the exact error outperforms the bound by quite a lot more for our method than for the canonical method, which is an interesting observation. And we consistently saw that over all the molecules we investigated. And now to show you a summary of all the results we obtained, we have this graph where vertically we plot the ratio of either the error bounds or the exact errors of the canonical method to the error of our method for some given cost. So each individual line here denotes one specific cost. And the red bars here are the ratios of the error bounds, and the blue are the ratios of the exact errors. And you can see that it fluctuates quite a bit, but it hovers somewhere around 1 order of magnitude that our method is more accurate than the canonical one for these molecules. And for the exact errors, it's even more than that, which is what I mentioned earlier, that our method outperforms the bound by a lot more. So here it ranges from anywhere from 1 to 2 orders of magnitude. And you can see that these range over many qubits. So we have anywhere from 11 to 25, all the way up to 75 and 91 qubits for these molecules. And it seems to hold across all of them. And one last thing I want to draw your attention to is here in the bottom left corner, which is labeled random. We took lithium hydride, the Hamiltonian for the lithium hydride. We replaced all the coefficients in front with a normal distribution with a mean of 1 and a standard deviation of 0.1. And you see that all the advantage completely disappears when we do that. And we just get the same performance as the canonical method, simply because our modification relies so much on the fact that the distribution varies over many orders of magnitude. So in summary, we were able to show that by doing this simple generalization of the method, you could achieve quite a considerable improvement of the error over this canonical method that was introduced by Barry and colleagues, which might be important for actual simulation tasks. That's all I have. Thank you very much.
Thanks a lot. It was a nice talk. Yeah, so I'm looking at the channel, so if you have questions, feel free to post them there, and I'll forward them to Richard. So far, we don't have any, which might be a good sign.
Or not, who knows? Well, if there are any questions later, I'll still be in the Slack channel to answer anything that comes up.
Okay, perfect. Yeah, so I guess if there are no questions there, we can thank you again virtually in the Slack channel as I've started doing. So thanks again, and
okay. Thank you.